Modulo is one of those operators that seems simple at first, but then gets confusing, especially when you start talking about negative numbers. So today we're going to break it down step by step. We're going to do some examples, look at negatives, and then see how modulo actually shows up in the real world. Hi, and welcome to Rosie's STEM. Over 2 years ago, I posted one of my first videos, and it was titled Master the Modulo Operator Explained Simply, which quite unexpectedly became one of my most popular videos. And recently I got a comment on that video. Shout out to Harshitha T J4K asking, what about 1 mod -3? And there are two interesting things going on in that problem. First, being that the number we're dividing by, the divisor, is larger in absolute value than the number being divided. So we are taking 1 divided by 3. And second, the divisor is negative. So we're actually doing 1 divided by -3 and looking for a remainder. So Harshita's question prompted me to make a follow-up to that old video that talks about more complicated modulo problems and answers the question they posed in their comment. So if you aren't familiar with modulo or calculating a modulo problem on positive numbers, you might want to go ahead and check out my earlier video before this one. It's just about 60 seconds long. I will put it in the cards here and in the description down below, and then come back to this one for the more complicated problems. Let's get into it. All right, so let's talk about some modulo problems with negative numbers. First, recall that modulo looks for the remainder after division. So for example, 7 mod 3 is equal to 1 because when you divide 7 by 3, you get 2 because 3 goes into 7 twice with a remainder of 1 because 3 times 2 is 6 plus 1 gives us 7. A helpful way of thinking about this is to think about modulo as counting around a clock. If the modulus is 3, then we're counting around a clock that has 3 numbers instead of the typical 12. We always start with 0, and then we're going to count 7 steps around this clock. And that is actually going to land us at 1. So 7 mod 3 gives us 1. We can see that 3 times 2 gives us 6 plus 1 is 7. Now what happens when we extend this to talk about negative numbers? For example, -7 mod 3. The negative sign is going to signal us to count backwards around the clock. So instead of counting clockwise, we're going to count counterclockwise. So we're going to still count around that same clock that has 3 numbers starting with 0, but now we're going to count the opposite direction, which means we're going to end at 2. So -7 mod 3 is actually going to give us 2. And another way of looking at this is if we did 3 times -3, we would end up with -9 plus 2 would get us to -7. So that plus 2 would give us a remainder of 2 in this type of problem. Now, what if we were looking at 7 mod -3? So what if instead of the 7 being negative, the 3 is negative, our divisor? In math, modulo is usually defined only when the divisor is positive. So in modular arithmetic, we're looking for the remainder after division, and remainder is always between 0 and the divisor -1. We don't usually consider a remainder to be able to be negative, but the percent sign in Python is not actually pure math modulo. So Python doesn't consider this problem undefined. It will give you an answer to your problem. And it calculates it by moving counterclockwise around the clock, just like we did previously. So we're counting around the clock counterclockwise. We're going to end at 2 again. But Python always makes sure that the remainder takes the same sign as the divisor. In this case, our divisor is negative, so it's not going to say the answer to our question is 2. It's actually going to give us -2. So in Python, 7 mod -3 is -2. Another way of thinking about this is -3 times -3 gives us 9. And then if we subtract 2, we end up at 7. So we can think of -2 as being that remainder when we divide by -3. So the key here is to remember that in Python, the remainder always takes the same sign as the divisor. With -7 mod 3, our divisor is positive. We end up counterclockwise around our clock, and at 2, that has the same sign as our divisor, so the answer is 2. In this case, our divisor is negative. We count counterclockwise around the same clock. We end up at 2, but we have to give the answer -2 to make sure it has the same sign as our divisor. So that brings us back to our original question. What about 1 mod -3? So we're looking at the remainder after dividing 1 by -3. If we are in Python, we will get an answer. If we're talking about pure math, we would say that this question is undefined. But then here we can count around the clock. We would count counterclockwise because we're working with a negative number in our modulo. We count 1 around this clock counterclockwise, and we end on 2. But we're going to give the answer -2 because we have to make sure that we have the same sign as our divisor, which is in this case negative. So we can think of this as -3 times -1 gives us 3, -2 gives us 1, so that -2 there is a remainder. So the answer to the original question is -2 if we're talking about modular arithmetic in Python, or undefined if we're meaning this in pure math terms. So there are actually a lot of real-world applications of modular arithmetic like this. The first is thinking of clocks and calendars. So I mentioned this in my short, but you can think of military time and converting between that 24-hour and 12-hour clock as being a modular operation. So if we talk about 1500 or 15 o'clock in military time, that's really 3 o'clock in 12-hour time, because if we do 15 mod 12, we're going to end up with 3. Think about counting 15 around a normal 12-hour clock. You're going to end up at 3 o'clock, so it would be 3 p.m. Days of the week also follow a modular pattern, right? There's 7 days of the week. If we're talking about starting on Tuesday and adding 10 days, that's going to be 10 mod 7, 3 days later, which lands you on a Friday. So those are both different ways of using modular arithmetic in real life. Any repeating cycle can actually be thought of in terms of modular arithmetic. So imagine you're playing a 2-player game, we're on turn 7, and you want to know which player's turn it is. We could do 7 mod 2, which would give us 1, and that would mean that it's actually player 2's turn. Remember, for modular arithmetic, we're always starting counting from 0, so if the remainder were 0, it would be player 1's turn, but we have to go 1 further. The remainder 1 gives us player 2's turn. Modular arithmetic is also used a lot in computing. So if you have any familiarity with hashing or hash functions, modulo is usually used to keep numbers within a certain range. For example, if we're sorting data into 10 buckets, we would use mod 10 to kind of decide which bucket that data is going to go in. That way, no matter how big our number is, it's always going to fit into one of our 10 buckets because we're going to take it mod 10. It also helps with error detection. Think of an ISBN number on a book or a credit card number, and you're trying to check a credit card. You can use modular arithmetic to detect typos and make sure that the remainder actually matches a particular rule that governs what ISBN numbers or credit card numbers should look like. So to make sure it's an actual valid ISBN or credit card number. Modular arithmetic even shows up in surprising places like music. So there's 12 notes in the Western scale. So notes wrap around mod 12. If you go up 15 steps from a C, you can think of that as 15 mod 12 equals 3, which is going to land you on a D sharp. So that's the math behind things like octaves. So it's not only math and computer science, you can also see it in art and music. It's not really just a math trick. It's how we keep repeating patterns under control. And the only confusing part really is negatives, but if you remember that rule in Python that the remainder takes the divisor's sign, you'll always get the right answer. So modulo isn't just a math trick, it explains clocks, calendars, rotations, data storage, error checking, and even music. It's how we keep repeating patterns under control, and we can use the rules behind modular arithmetic to help us with things like hashing and error checking. So if you remember the rule, the remainder takes the divisor's sign, even when we throw negatives into modular arithmetic, you'll always get the correct answer. Just remember that Python works a little bit differently than the pure math version of modulo. If you learned something, please give this video a like and subscribe if you haven't already. And if you have questions or thoughts for future videos, please put those in the comments and yours might be the next video topic. So thanks for watching, and I'll see you in the next one. Bye.